All right, so let's try example number 1. So we have a few list of items that we're looking for. So we're gonna go through every single item. So the function is given 2x cubed plus 2x squared minus 12x minus 18. And the goal is for us to analyze and the function and then sketch it later on. So let's begin by first finding the first derivative, and that's pretty straightforward in this case. This is just using constant multiple rule and the power rule. So 2 times bring down the power, 2 times 3 is 6 times x, and then subtract 1, so that's 2, plus, and then bring down the power and multiply that. That will be 2 times 3, that's 6, minus 1 is x, and then minus 12, and we drop the x, right? And then the derivative of minus 18 is 0, so we don't carry that. All right, so that was part A. Now let's find part B. The part B is asking us to find the critical numbers. Remember that critical numbers are found whenever the first derivative is 0 or when the first derivative is undefined, and we look for and we solve for x, right? The x is these are considered to be the critical numbers that satisfy these conditions. So in this case, there won't be no undefined. The reason why is because this is a polynomial, and polynomials are defined everywhere, right? So the derivatives are defined everywhere. So the only case is here to find where find x such that f prime of x is equal to 0, right? Solve for x. All right, so what we're gonna do here is we're gonna focus on the right side equality and solve for x. If you guys are thinking about how do we solve this, well, recognize that this is a quadratic function, and we often try to factor this out. And if you guys are saying, well, how can we factor this trinomial? Well, first begin by factoring any greatest common factor. In other words, if you guys see, every term has a 6, a factor of 6, and we carry the 0 there. And now if you guys think about it, we can factor this one much easier by because it's a trinomial. This will give you a factor of binomials, right? X times x minus or plus something times the quantity x minus plus something, right? So two numbers that when you multiply gives you negative 2, but when you add them gives you 1, and I'm thinking about plus 2 minus 1. And so there you go, right? We have factored this out, and then from here we're going to use the zero factor property to isolate these two, and set them equal to 0, right? And then that implies that x plus 2 equals 0. By subtracting 2, we get x equals negative 2, and the other one is by adding 1 gives us x equals 1. So these are the possible critical numbers, and how do we confirm whether these are critical numbers? Well, they have to be part of the domain of the original function, and they are, because this is a polynomial, and polynomials, the domain of polynomials is all real numbers. Hence, these two are real numbers, so therefore these are critical numbers. So critical numbers are found. Okay, all right. So let's find the next part is to find the intervals of increasing and intervals of decreasing. For this, we're gonna have to create a number line and use any critical numbers or any undefined values or any vertical asymptotes. In this case, we don't have any vertical asymptotes. We just have critical numbers. So let's go ahead and jump in and do a number line. All right, so we're going to use the two critical numbers. Since these are critical numbers, we're trying to figure out what is the value of the derivative. Well, we do know what the value of the derivative is because these are critical numbers and they were found when the derivative was 0, right? So at x equals negative 2, the derivative is 0. And when x equals 1, the first derivative is 0. But what we need to do is we need to test what's on this side. So we're going to test a number, any number on the left side of -2, a number between -2 and 1, and any number on the right side of 1. And there you go. So I just randomly choose any number in those intervals, and what we're going to do here is we're going to test them. So how do we test them? We look at the first derivative. We could use the original derivative that is right here, but that's not convenient. It's actually much convenient for us to use this one right here. This is the derivative, is just in a factor form. And why do we choose to work with the factor form? I want to remind you is because we're only interested in whether this is a positive or negative, positive or negative, positive or negative, because if the derivative is positive, that means that the function is increasing. If the derivative is negative, that means that the function is decreasing. So we only care whether this is positive or negative. So we're going to test -3. Now, 6 is a positive number, right? So we know it's a positive number. When you plug in -3 here, -3 plus 2 is going to give you -1. So that's negative. And then plug in -3 here, and that gives you -3 minus 1. That gives you a negative number. So what we're doing is you have pretty much multiplying numbers that are a number that's positive, a negative, and a negative number gives you a positive number. Remember that if you count the number of negatives and the number that your count is even a number of negatives, then your product will be positive. And you guys notice this is much easier than trying to figure out whether what's the actual number, right? And multiply them, because we only care about the signs. We don't actually need to know that this is a positive 6. When you plug in a 0 in here, you're gonna get 0 plus 2. That's 2, but it's just a positive. When you plug in a 0 in 0 in here, that gives you 0 minus 1, which is -1, which is just a negative. Again, we're multiplying. You're multiplying this, so this will give us positive times negative, gives you a negative. So that's the reason why we're using the factor form. This wouldn't work if we would have used this instead, right? This we would have to actually use the entire. We actually have to find the actual number, the end result of this. But for here, we just have to play around with the signs. All right, and the last one is f of 2. So we have 6 is a positive number. 2 plus 2 is positive. 2 minus 1 is also positive. So positive times positive times positive is positive. So if we go back over here, oops, we already know what is the outcome. Is positive here and here, anywhere there, and between -2 and 1 is going to be negative, 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 and positive, 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 anything after 1. So if we look at the actual function, right, the function is increasing horizontal at this critical number, decreasing horizontal, and then increasing, right? So if the question is to find the interval for which the function is increasing or decreasing, so we're going to say that it's increasing between negative infinity all the way to -2. And then we jump the other way, and then it's going to be from 1 to positive infinity. And then don't forget to put the union symbol. And then it's decreasing between -2 and 1. Right? If you think about it, that's a place where the function is decreasing. And there you go, right? So we found that part. All right, so now the part D is asking us to find the second derivative. So let's go ahead and do that. The second derivative by looking at the original function. Can we have a well, all we have to do is take the derivative of the first derivative. So we don't want to use the factor form, because then we would have to use product rule. We can just go ahead and use the original first derivative, right? So the derivative of the derivative will be the second derivative, which will be 6x squared. I'm looking over here. So bring down the 2. That'll be 2 times 6 is 12. And then plus 6. We drop the x, right? And then the minus 12 goes away, right? The derivative of a constant is 0. So there you go. We found the second derivative. Now the next part is for us to find, identify any maximum or minimum for this point. We already know that we have two critical numbers. Critical numbers are x equals -2, comma x equals 1. So these are the only possible places where we can have a maximum or minimum, right? So what we need to do is we could look at the graph right here, and we can visualize that since we already did all this work, we can see that at x equals 2, this is going to be a maximum, and then at x equals 1, this will be a minimum, right? So it's kind of neat that we already have this picture here. So let's use that information. So it's a max at x equals -2, and is going to be a min at 1, right? X equals 1 at x equals 1. Now we got to be careful though, because they're asking us to find the maximum and minimum as points. So what we need to do is find the corresponding y value for each one. How do we do that? Well, we know that the original function is the same as your y, right? It's the y component of your x. So all we gotta do is plug in -2 into the original function. So let me do that right here. I'm taking the original function and plug in -2. And if you put this in your calculator, you should be getting the value of 2. So the maximum is going to be the point -2, comma 2. For the minimum, we're going to have f of 1 plug in at 2 times 1 to the third plus 3 times 1 squared minus 12 times 1 minus 18. And then this gives us f of 1. And this will give us a value of, if you put this in your calculator, should give us -25. Is it -25 or +25? Let me double check my number. Right, 2. Minus 12 times 1 minus 18. Alright, yeah, it's -25. Alright, so we got our number. So the point is going to be a minimum point 1, comma -25. Alright, so x and y, x and y. Alright, so move on to the next part. Remember that, so just real quick, because we always get this confused. This is x is the location of where your max is located. The actual maximum value of the function is 2. Again, this is the location where you're going to find the minimum value. The actual minimum value is -25. Right? And then we're talking about here local max, local min. All right, so moving on to the next part is asking us to find the second derivative. Use the second derivative to identify the intervals where the function is concave up or concave down. So let's go ahead. We already know this. The second derivative is going to be 12x plus 6. Remember that we get we know for us to sort of separate this concave out, concave down. This is going to happen whenever the second derivative is 0 or when the second derivative is undefined. So what we're going to do here, well, we know that this is never going to be undefined because this is a polynomial. And so this is defined everywhere. By the way, this is double prime. All right, so well, the only option that we have here is to set this equal to 0 to find the 0 of this function. Now what we can do here is we can factor again. If we want to, we can factor 6, 2x plus 1 set equal to 0. And this implies that 2x plus 1 equals 0, right? By dividing both sides by 6. And then solving for x, minus 1, 2x equals negative 1, divided by 2, divided by 2. And then, so that implies that x equals negative 1/2. All right, so we have our line here, our number, and we're gonna use this to create the number line. I may not have enough space here, so let's see if I can minimize some of my notes. All right, and then move this here. There you go. All right, so the number line that we're gonna have here to find the concavity of the function is gonna depend on negative 1/2, right? And any vertical asymptotes, but we already mentioned that there's no vertical asymptotes, so there you go. So this is your x value, and what we're looking for is the actual value of the second derivative. Since the way we found this possible point of inflection is by setting the second derivative equal to 0, we already know that this is going to be 0 for the second derivative. So what we need to do here is just figure out what is happening on the left side of negative 1/2, which we can use negative 1, and on the right side of negative 1/2, which is we can use 0. So now that we have this, we're going to go ahead and test these numbers. So we have 6 times 2x plus 1. When you plug in negative 1, we end up getting positive times, we plug in negative 1 in here, we get negative 2. Negative 2 plus 1 is negative number, so that gives us negative number. When you plug in 0, we get positive, and then 0 times 2 is 0, so plus 1 is positive. Right, so I'm just figuring out what is the sign value. Again, that's all we need to know, right? We just need to know whether this is positive or negative, so we end up having negative and positive here. For the function, this implies that because the second derivative is negative, that means it's concave down. And because the second derivative is positive on the right side of negative 1/2, the function is concave up. And so the conclusion is that is concave down for the interval negative infinity to negative 1/2. And you guys can kind of see that, right? And then concave up from negative 1/2 to positive infinity. And so we end up getting open intervals always, and this is going to be positive infinity. Now I want to remind you, or just I want to make a note that the way that I do this is I circle my critical numbers because I often make a mistake here, right? So it just keeps me on the record that when I'm separating my intervals, I'm going to be using the numbers that are circled. Now I also want to mention that this process is very similar to what we did with the critical numbers, right? It's very similar, critical numbers, and when we find when the function was increasing, decreasing. So what I always tell my students is the same thing, right? We're doing the same thing that we did with the first derivative, but we get different information, right? We get different information. Whether with the first derivative we get whether the function is increasing, decreasing. With the second derivative we get whether the function is concave up or concave down. All right, very nice. So let's move on to the possible point of inflection. Since there's only one point here, we have one possible point of inflection, and that's x equals negative 1/2. And actually, because at that point we changed concavity from concave down to concave up, that means that this possible point of inflection is an actual point inflection point. So it is an inflection point. It is going to give us an inflection point, but in order for us to give us a point, we need to find the corresponding y value. So what we need to do is go back and plug this into the regional function. So the regional function is going to be, let me just get my notes here. So we have 2 times negative 1/2 to the third power plus 3 times negative 1/2 to the second power minus 12 times negative 1/2 to the first power and minus 18. When you do all these computations, you should be getting something in the negative 11.5. So the point is going to be negative 1/2, negative 1/2, comma, negative 11.5. Also, you can just have a negative 1/2, comma, 23, negative 23 over 2. All right. So very nice. So we got all the information, right? One of these, right, is the inflection point. All right. So now what we need to do is find this, upload a sketch, or in this case, write the sketch. But we're also asking us to do some X-intercepts. So remember the X-intercepts are found by doing X-intercept is found by finding X when Y equals 0, right? Remember the X-intercept is this right here. This is the X-axis. So we're looking at points that are intercepting the X-axis, where the value of Y happens to be 2, 1, 0, right? So Y is 0 always at the X-intercept. That's why we set up equal to 0. And so let's find it out, right? So if you have the function in front of you, the original function tells us that we have so we have the function 2x cubed plus 3x squared minus 12x minus 18, right? And so we're gonna set y equals 0, which is, this is your y, so that means we're gonna set that equal to 0. So we're gonna focus on the right side equation and or equality to solve for x, right? Solve for x. So this is kind of odd, but this is a long function. But one of the techniques that we learned in factoring was factoring by grouping. So what we're going to do here is we're going to focus on the first group and focus on the second group independently of each other. So what we're going to do is look at the first group and look at what do they have, what common factors do they have. And obviously x squared is a common factor between both of them. If you factor an x squared in those two first terms, then you're going to get left with 2x plus 3. And if factor by grouping will work, then that means that you must have a 2x plus 3 as well here, right? So what you need to do is figure out whether this is a plus or a minus and figure out what the number goes there. So if factor by grouping is going to work, then you have to figure out what kind of number you need outside. So when you multiply, it gives you negative 12x. Well, you have a 2 inside, so 2x times negative 6, or in other words, minus 6, will give us minus 12x. So let's double check, make sure that that works with the next term. So negative 6x times 2x gives us negative 12x. That's good. Negative 6 times positive 3 gives us negative 18. So that seems like that to be working. And otherwise, this wouldn't work. So what we're going to do now is we're going to factor the group. If you notice, we have two terms here. And both terms have a common factor of 2x plus 3. So we're going to factor that out. So that becomes 2x plus 3. And what's left behind? X squared minus 6. All right, so that's what we end up getting by the zero factor property. 2x plus 3 equals 0, comma, x squared minus 6 equals 0. We solve for x on both of them, minus 3, 2x 2x minus 3 plus 6 plus 6, x squared equals 6. Divide by 2, square root both sides, plus or minus, and then we end up getting x equals negative 3 halves, and x equals plus or minus square root of 6. All right, and so that means that we have two x-intercepts. That means when y equals 0, your x equals negative 3 halves, comma, square root of 6, 0, and negative square root of 6, 0. Actually, we have three x-intercepts. All right, and then lastly, we're gonna find the y-intercept. The y-intercept is very similar, right? A y-intercept implies we're looking for y when your x is 0. So that's actually much easier for us to do because all we gotta do is replace x with 0. Which is 0, 0, 0 equals minus 18. So y equals negative 18 when x equals 0. All right, so these are the intercepts of the function. What we're going to do here is we're going to actually find where that happens. So negative 18 is beyond this scale. So that might be somewhere down here. And then we have negative 3 halves is 0. Negative 3 halves, that's negative 1.5. So that's 0 right there. And then we have these square roots. The square root is roughly somewhere, by using the calculator, is roughly around 2.4, right? 2.44. So we can't be that accurate with those two, right? Because we have a limitation in our technique of drawing and accuracy. So what we're going to do is we're going to use 2.44 to roughly say that that's where the function will be. So 2.44 and negative 2.44 will be somewhere around here. And 2.44 will be somewhere around here. Right? Right, just roughly. And then what else points do we have? We do have also a critical number at negative 2, 2. So that's that critical number. And we also have a critical number at 1, negative 25. All right. So negative 125 will be somewhere over here. And then lastly, what else do we have? The inflection point, right? The inflection point happened in negative 1/2, negative 11.5. Negative half at 11.5. So somewhere in here there is an inflection point. All right, so we got everything we need. What we need to do is pass through those points. I would say that we want to maybe and come back and draw the points of the graph. So again, this is just a rough picture, and this is supposed to be a critical number, so we're going to be smooth there. And then this is where it changes from concave down to concave up. And then it hits this point right here, and then it goes up. All right, let me try that one. All right, and it keeps going that way, right? What I would suggest here is to write down the labels of the points. So for example, this is negative square root of 6, comma 0. This point over here is negative 2, comma 2. This point here is negative 3 halves, comma 0. This point here is supposed to be negative 1/2, comma 23 over 2, negative. And this is supposed to be negative, So 0, comma, negative 18. This is supposed to be positive 1, comma, negative 25. And then this was supposed to be square root of 6, comma, 0. All right, so that way, whenever we are doing, whenever we are drawing our pictures, at least the reader will know that that's what the intention is when you're drawing those pictures, right? Because we're not gonna be that accurate, but at least we can properly put the correct labels. All right, so this is how it looks like, right? The sketch of the graph, how we generate the information. Again, this is time consuming, but it's important for us in order for in this course for us to understand